Welcome to week 4 of vibrations lecture. In this lecture, we will try to move ahead. We'll start with a small recap what we were doing earlier with regard to when we started looking at multi-degree of freedom systems, and we talked about Lagrange method. In the last year, you had looked at Newton method, and in this year we started saying that we'll move away from Newton method and look at Lagrange method. Before we move ahead, let us try to understand what is the crux of the problem that we are trying to solve. So what's the crux of the module? Right? So we have any physical system, okay? So let's say we have any physical system. Let's say the physical system could be your F1 car, right? Maybe it could be the front wing, or it could be the rear wing. It could be a wind turbine blade. It could be, let's say, a wind turbine blade. It could be an aircraft wing, right? It could be a helicopter rotor. All of these can be approximated in simple sense. Let's say I can approximate all of these. All of these have some specific characteristics that I would say length, breadth, and thickness. Most of these structures, if you think about it, the length is very much larger, then breadth is very much larger than the thickness. All of these structures, if you have thought about it, they kind of move, right? For example, let's say if you think of an aircraft wing, let's say if this was our aircraft wing, we can say that, let's say it's fixed at one end, while the other, as you fly through the aircraft, it is kind of moving. The same thing, what we are trying to understand in this entire module is to see how can we characterize and write this motion, which is a periodic motion, in a mathematical format. Let's say all these structures move, and they don't move in any way, but they move periodically about a mean. Our goal in this entire module, let's say goal of the module on vibrations, how to express this motion mathematically. Right? So for example, we have already established that we can write something like m into x double dot plus c into x dot plus k into x equal to set of forces, right? So we said this was our mass matrix, our damping matrix, our stiffness matrix, and our force vector, right? So we have our acceleration, velocity, and our displacement, right? So if I know any object and I want to characterize how is it moving, and for example, the aircraft wing might not have the same stiffness as a Formula 1 car as a wind turbine. So we want to understand when the stiffness of the material when the material changes itself, the stiffness changes, how is it going to affect the overall behavior of this wing? For example, the mass can change. The mass can be different for each of these. For damping can change. So when each of these changes, how can we manipulate that, and how do we understand the motion of each of these objects? What does this simple equation allow is that it allows us to manipulate things to test out, iterate, and get a good preliminary design from where we can start more complex modeling and so on. Right? So our whole crux of the module is to derive equation of motion. Let's say our crux of module, given any physical system, how to derive the equation of motion. The equation of motion, right? I'm going to use EOM going ahead, so that I don't have to write equation of motion every time. So our whole thing that we would spend all our time largely is to understand how do we derive this equation of motion. Okay. So once we know the equation of motion, we can always use some kind of MATLAB or Python code in order to solve this equation of motion. But knowing how to approximate a physical system and write a simplified equation is very important before we can go and solve it with MATLAB or something. At this point, one would ask, why can't I just ask ChatGPT to kind of approximate it? Even to ask ChatGPT, you need to know what you're asking it, right? For example, let's say if we go back to our aircraft wing. So let's say this was our aircraft wing. Aircraft wing is not just moving up and down, but it's also having a torsional motion. So if you observe it very carefully, it is basically having a very complex motion, which includes both the transverse vibration, which is up and down, also the torsional vibration, which is the rotational motion about the hub. So now you need to understand what is this system doing, how is this system moving, and what can we do before you can even ask ChatGPT what you need to get from it. And that is why this module is very important and focuses largely on how to derive and get this equation of motion rather than solving the equation of motion. Solving the equation of motion, once you have an equation, you can always give it to MATLAB or ask ChatGPT, how do I solve this matrix equation, and it's probably going to help you with it. But if you don't know how to get this equation itself, then it would not be possible to understand how systems behave, right? So let's kind of move back and just recap what we had done previously. So let's have a quick recap from last week. In last week, we had considered a simple two-body system, say M1, and we had two masses, M2. Both of these are lying on some kind of a frictionless surface. Right, K1 and K2. We define some generalized coordinates x1 and x2, right? And we eventually derived that the equation of motion for this system is m1 x1 double dot plus k1 plus k2 into x1 minus k2 into x2 equal to 0, and m2 x2 double dot minus k2 x1 plus k2 x2 equal to 0. Or we recast this into a matrix form, right? We put this into a matrix form and we said m1 m2 into x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2 k2 into x1 x2 equal to 0. So what we had here was a system of free vibration. So we also recast this. We could write this as m into x double dot plus k into x equal to 0. So this was nothing but our free vibration system, or free vibration, undamped free vibration. We don't have any damping. And so we essentially spent a big part of last lecture trying to understand how to, if we have a mass and spring system like this, how can we use Lagrange method in order to determine this equation of motion. We did not again go into solving this equation of motion. We'll come to that as we go into lecture 6, and we'll try to understand how can we solve these equations of motion in lectures 5 and 6. So now let's start to move ahead with it and try to think of realistic systems. Since lectures 2 and 3, we had some simple systems like this, and we used the Lagrange method in order to get this equation of motion, right? So now let's try to see, okay, if we had an actual physical system, like let's say an aircraft wing, how do we approximate that into an MDOF, or a multi-degree of freedom system, that we have studied in lectures 2 and 3. In order to do this, we'll look at very simple structures like a beam. Like we said, when we started our lecture, we said that all of these very complex applications are dealt with assuming that we have some kind of a beam structure where the length is very large compared to the breadth is very large compared to the thickness. So why are we interested in beams? One, because you already have some fundamental knowledge of beams which you studied in structures 1. So in structures 1, you have already looked at various beam structures where you looked at beam bending. So you had a beam and you applied some kind of a point load and got the deflection, or you applied a uniform distributed load, got the deflection, right? So for example, let's say if you have or a simply supported beam and so on. So since we already have some background in this, we would like to see how to use this background that we have and build on it rather than starting something new from scratch. But before we build on it, we might want to just recap some of the things that we have so that we can use in the later lecture as we go along in the part of this module. Okay, so just a recap of the beam, recap of structures 1, right? So let's assume that we have a simply supported beam. So we have a beam, right? So let's say this x direction and this is the y direction, right? So the length of this beam is L, and flexural rigidity, we'll introduce what flexural rigidity in a moment, is E unto I, right? And we, from structures 1, we know that if there's a point load of magnitude P applied, so let's say point load P is applied, that would imply the deflection is nothing but the deflection of the beam is nothing but P into L cube over 48 EI. Okay, and we know that the second moment of inertia, I, is nothing but our second moment of inertia. And for, let's say, if we had a rectangular cross section, and for rectangular cross section, so this can be equal to BH cube by 12, right? And E is nothing but our Young's modulus, so that we are all clear and on the same page. E is our Young's modulus. Okay, so now the question comes in, so what would happen? Why is E so important, right? So for example, let's think of a physical situation here before we go ahead, and let's go back to our steel ruler that I've been using. So I've fixed the steel ruler at one end. Let's say I'm going to assume I'm going to apply a point load, right? So I'm applying this point load along the direction of thickness, and very small load, I get quite a big amount of deflection, right? So now let me just turn it around and apply it along the length of the breadth, right? So a significant amount of resistance and very small deformation for the same amount of load that I might apply, right? You can see it's very small amount of deflection. So you would see, for example, let's say if we consider the breadth to be, so if breadth was about 2.5 centimeters and our thickness was about 0.01 centimeters, which is about approximately the same dimension of the scale, then we can find I is nothing but BH cube by 12, right? So we can see for the two cases, the ratio of I is approximately about 10 to the power 7. If we are considering the case of loading across the thickness versus loading across the breadth, right? So then B and H would interchange and the moment of inertia would be significantly different. So that is why the moment of the flexural rigidity has two parts to it. One is the geometric stiffness that discusses about, that talks about, let's say, some kind of how the material is distributed across the neutral axis of the beam, and also some aspect of the material stiffness itself, which is the Young's modulus. Together, E into I provides a unified measure of the structural rigidity of the structure. Now let's go ahead and try to draw the free body diagram. So we have been used to writing a free body diagram for most of this situation. So let's consider our beam. For example, we have our beam. If I would take some infinitesimal element, let's say of the size dx, and this is at some distance x, from the left root, and let's say the length of the beam was L. We are just doing this so that we recap what we have done and we can reuse that. So if I'm going to rewrite this infinitesimal element dx, I can say that there's probably a shear force acting V, and on the other side it is V plus dou V by dou x into dx. Similarly, if I have a bending moment M, I also have a bending moment on this side, that is M plus dou M by dou x into dx, right? And since we are interested in dynamics, I can say at the center of the infinitesimal element, I have an acceleration acting as well. So I can say rho into A into dou square y by dou t square, right? So I can assume that there's some kind of an acceleration effect also acting along that center of the element. So if I was to write the equation summation of forces F along y direction equal to 0, I can say V minus V plus dou V by dou x into dx, right? So V is acting upward, I'm taking positive. On the right hand side it's acting downward, I'm taking negative, minus rho A into dx. So rho A into, sorry, there's probably a dx here that I missed here. So rho A into dx into dou square y by dou t square. So rho is nothing but our density, A is nothing but the area, cross-sectional area, and dx is the length of this small element. So density into area into length is nothing but density into volume, gives us the mass, right? Rho A dx into dou square y by dou x square, that is equal to 0. Or in other words, I can write, if I simplify this, I have minus dou v by dou x equal to rho A dou square y by dou x square. So let's keep this here for a moment. Let's call this equation number 1. So similarly, we can also write the equation of moment equilibrium, summation of m equal to 0. Right? I can, just to make my life simpler, I'm going to take the summation of moment equal to 0 at the left end of at the center of the element, right? So then I can easily write things as, so I can easily simplify things, or I can take it on the left end of the element, so I can simplify things very easily, or maybe right end of the element, either of them can work, right? So it doesn't matter where we are taking the moment equilibrium, we'll probably get the same solution, okay? So I can, if I rewrite this, I will have V into dx plus dou m by dou x into dx equal to 0. Our that simplifies into our shear force is nothing but the change of moment. Okay, I'll let you to derive all the steps. I'm just giving the simplified version so that we can try to move ahead. So now I have some relation that relates the shear forces with the moment, and I can substitute that from equation 2 into equation 1. Substituting 2 into 1, we have minus dou by dou x by dou x equal to rho A dou square y by dou x square, sorry, dou t square. It's a time derivative because it's acceleration, right? So that implies I have dou square m by dou x square rho A dou square y by dou t square, right? So but we also know from our structures 1, right? So we have the relation from structures 1, we know m is nothing but ei, for especially for a linear elastic homogeneous material, dou square y by dou x square. So if I substitute back, that I have minus ei dou to the power of 4y by dou x to the power of 4 equal to rho A dou square y by dou t square. Okay, so this is nothing but, or I can rewrite this as dou to the power of 4 over dou x to the power of 4 equal to minus 1 over alpha square into dou square y by dou t square, where alpha is nothing but square root of rho a over, sorry, ei over rho a. Right? So essentially ei is kind of some kind of bending stiffness that and rho a is mass per unit length that resists acceleration. Ei resists curvature, and essentially overall it gives some let's say flexural rigidity to inertia ratio parameter. That's what our alpha would be. Okay, so let's keep this now. So one of the things that we see, what we have here is a fourth order equation. So we have a fourth order equation. So we can always solve this fourth order equation, which will come into lecture 6 when we are going to solve how to solve this fourth order equation. But for now, let us see if we can simplify this fourth order equation, and could we simplify, and are we going to be able to use the simplified version and use some of the knowledge that we have gained in terms of multi-degree of freedom system to write our equation of motion. We are not focused on solving the equation of motion, we are focused on writing the equation of motion, right? So our question, can we, let's rewrite this. Instead of solving the fourth order equation, can we write a more simplified equation like mx double dot plus, let's say, kx. I'm just going to for now equal to 0 and convert it to an MDOF system. If I can convert it to an MDOF system, that means that I am able to use that, and I will be able to use this all the knowledge that I have developed as a part of the MDOF system itself, right? So that is one of our motivations, and we'll try to see how to do the same thing when we have torsional vibration, longitudinal vibration, and so on. But for now, let's look at the transverse vibration, and from there go ahead with it. Okay, so now we have let's say we have assumed that we kept telling that we have some kind of a beam structure that we would like to use. So this beam structure could be anything. It could be a airfoil aircraft wing, it could be a Formula 1 car, it could be a wind turbine blade, it could even be bridges, right? So our application is not necessarily aerospace engineering with aircraft or helicopter blade, or is not necessarily wind turbine with mechanical engineering, or it could even be as much as bridges with civil engineering and so on. So the applications are very wide. So let's start with a very simple structure. So let's say we assume a cantilever beam, because cantilever beams are nice and we kind of use it everywhere. So let's say we do and this idea and exercise for a cantilever beam, and then we can always really use the same ideas for everything else. So let's say if this was some kind of a structure with some payload, let's say some payload, and let's say this was our structure, right? So our whole idea, so this is our real structure, real physical model. And we want to approximate into a multi-degree of freedom system. So we have a beam, and we are going to approximate into some set of discrete masses. Okay. So let's say we assume, for now we'll just assume 3 masses, and later we will see what would happen if you increase the number of mass and so on. We want to just have something that is very easy for us to work with, so we will just use 3 masses so that we can derive and see things. Okay, so this is our x direction, This is our y direction. I would say this is mass m1. Let me write it on top. So let's say mass m1, m2, m3. So each of these have some degrees of freedom. I'll assume that it's only there's a transverse motion up and down. So I'll call this as y1, y2, y3. This is very similar to our spring system where we had seen that it's moving in the x direction, but here we are saying that each mass is moving in the y direction. Right? So we assume that the lengths of each of these segments are constant. So S1, S2, L3. So we say S1 is equal to S2 equal to S3 is nothing but L by 3, where L is the length of the entire beam. Okay. So our goal is to take this complex physical structure and let's say this is our approximated MDOF system. So once we know our MDOF system, we know the equation of motion. So we know the equation of motion would be some kind of a mass matrix. I don't know what that is yet. So y1 double dot, y2 double dot, y3 double dot. For now, let's assume that we only are looking at undamped free vibration. So let's say undamped free vibration. So then we have some stiffness into y1, y2, y3 equal to 0, 0 and 0. So the question comes in, if we want to express this complex structure as a simple beam with some masses so that we can use our idea of MDOF system, then we need to know what is this mass matrix and what is the stiffness matrix. So what are they? So our big part of the lecture today is what we will focus trying to understand how do we get this mass matrix and how do we get this stiffness matrix. Okay, so our goal for the day, determine given a physical system here we are using a cantilever beam, how to obtain mass matrix and also obtain stiffness matrix. If I am able to obtain the mass matrix and the stiffness matrix, then I am able to get this easily system of equation. I can solve that to get eigenvalues and so on and so forth, which would essentially give me the natural frequencies of this system. Right? So let's try to define some things before we go ahead. So let's say we define mu is density into area. So that is nothing but mass per unit length. We'll see why we are going to this makes our life easier to write things, and that means that the mass of each segment, I'm going to just write as m seg so that I don't have to write that, is nothing but mu into length of the segment, nothing but the length of segment, and there's nothing but the mass of the segment. Right? And we have said that length of the segment is nothing but L by 3, where this is nothing but the length of the beam. Right? So for now we just said it's all of these segments are equal length, but in general you can have different lengths of the segment and so on and so forth. So we will use an approach that is called as a lumped mass matrix. So we'll use this idea of mass lumping in order to obtain the mass matrix. So what is our question here? To get a mass matrix means we need to determine what is M1, M2 and M3, right? So we don't know what M1, M2 and M3 are. We know the mass of the total structure. We know the density of the total structure. Assume it's homogeneous and isotropic. We know the area. We know the length. So we know the total mass of the structure. But how do you put this total mass into three separate masses that are M1, M2, M3? That is something that we still don't know yet. So we have this total beam and we want to kind of, let's say, approximate this. So here the mass is distributed in every point. So if I take a point here, it has some mass. This point has some mass. Some point has some mass. It is continuous. So it's like one can say you have infinite number of mass points. We want to take this infinite system and say that mass is only here and here and here. There's no mass here. Mass is only here, here and here in discrete system. That means that we need to say if this is the total mass of this beam, how do I kind of take it and put it into M1, M2 and M3? Can I just divide by 3? Probably not. We'll think about why do we do this. In order to do this, we'll look at what's called as a load sharing approach. Okay. In order to determine that, question is what is M1, M2 and M3? Given total mass of the system, what is M1, M2 and M3? Okay, so we will use what's called as a lump load sharing approach. Okay, so what are we saying in a load sharing approach? We are saying, let's say we rewrite our beam. So we have a M1, we have M2 and we have M3. What am I saying? I am saying that if I was to take this segment and divide each of these into equal parts, okay, then each of these mass should be equal to the sum of the mass of the segment which is adjacent to it. For example, M1 has only one segment that is adjacent to it, while M2 and M3 both have two segments that are adjacent to it, right? So it's a very simple idea that whatever mass was there in this overall system, we are converting that into mass of each segment. Once we have the mass of each segment, we are taking the half of the mass of the segment, giving it to the right side node, taking half of the mass of the segment and giving it to the left side node. In addition, what we are just saying is take the mass of the segment, half goes to the right node, half goes to the left node. So if the mass of the segment is constant, then it's m by 2. Now the mass of the segment need not be constantly distributed. It could be possible that the mass at the root is much higher than the mass at the end, in a way, right? So in that case, maybe each of these masses might not get equal amount of load, equal amount of mass. Let's try to write this down, what the M1, M2 and M3 would be, and then we can see, right? So let's say M1 is nothing but mass of segment 1 or half of the mass of segment 1, right? So if I would write that half into mu into length of the segment, right? That's nothing but half mu into L by 3, that's nothing but mu L by 6. Similarly, M2 has half mass of segment 1 plus also half mass of segment 2, right? So there's something coming from segment 1 and there's also something coming from segment 2, right? So if I was to write that again, I have half mu, so or I can just rewrite this as half of each of these segments are equal, so I can write mu into L by 3, right? Let's rewrite this. So I get half of mu into length of segment 1 plus half of mu into length of segment 2, and that is nothing but half mu into L by 3 plus half mu into L by 3, that is nothing but mu L by 3. Similarly, again, mass of segment 3 is half of mass of segment 2 plus half mass of segment 3. So that's nothing but, I'm just going to directly write it here this time, but you can go back and try to check it out. So for mass 3, I have something from segment 2 and something from segment 3. So this was our segment 3, our segment 2 and segment 1. Okay, so that way we are able to find what are these three masses that are required in order for us to find the how do we distribute the total mass of the beam into discrete number of nodes. If you go back into the lecture notes and see, you will see, okay, what would happen if there are only 2 segments, 3 segments, 6 segments, 12 segments, and we can see that by the time we have about 12 segment, the error comes down to about 4% when it comes to the total mass, right? So I'll leave it to you to go back and just have a check on that. So, but now if we kind of use our idea from the MDOF system. So if you remember from our MDOF system, our mass matrix was M1 0 0 0 M2 0 0 0 M3, that is nothing but mu L by 6 0 0 0 mu L by 3 0 0 0 mu L by 3, right? Or I can pull this mu L out by, I can by 6 out, maybe 1 0 0 0 2 0 0 0 2. Okay, I can easily write this as my mass matrix. So going back, we said we want to convert our complicated system into a simple MDOF system, and once we know the MDOF system, we know what the equation of motion should be, right? Mass into acceleration plus stiffness into displacement equal to 0 for our free undamped vibration. So we said now we have used this idea of lumped mass in order to calculate what this mass matrix should be, and now we are going to further use, we left out, to determine what the stiffness matrix should be. Okay, so for our goal now is to determine the stiffness matrix. So once we know our stiffness matrix, our equation of motion is complete. So then we can always use any solution techniques that we have, like for example, it could be 4 lines on a MATLAB code in order to solve this equation of motion. So as I said earlier, our focus is all about how do we get to the equation of motion given any complex system. Then this equation of motion is a matrix equation, and there are lots of methods on how this matrix equation itself can be solved. So far we have used the Newton method and Lagrange method if you to determine our stiffness. So in your year 2, semester 2, in your dynamics module, you use the Newton method. This is very easy to do for simple systems. Newton method is probably gives you a very quick way of doing things. In our lectures 2 and 3, in here, we use the Lagrange method. This is again something very easy to do when you have discrete systems. Now lastly, for example, we were looking at 2 pendulum system. What if 2 pendulums, instead of string you had a spring, right? So these are discrete systems which you can easily probably approximate and try to be able to do these things. Now we can do the same thing with a beam as well, like we can put a torsional spring at the end of it and so on. But for now we'll try to introduce, let's say our lectures 4 to 5 here, we'll introduce the concept of stiffness coefficient. Okay, so we'll use this concept of stiffness coefficient in order to determine our stiffness matrix. Okay, so let's try to write the definition first, and then we will try to express what this means mathematically and how we are able to let's say get some physical meaning out of this. Okay, so what is the stiffness coefficient? Influence coefficient. Okay, or we define this with symbol Kij. Ij are subscript. We'll come back to what that is defined, okay, as the force at a point I, okay, due to unit displacement at a point J. So what I am saying here, if with all other points fixed, okay. So the whole idea comes from what's known as the Castigliano's theorem. We will not go into that at the moment itself, but we'll come back to see how it all fits into the picture, right? So if I had some displacement y at some point J, it causes some kind of force Fi, and the coefficient that relates these two is the stiffness coefficient. So if I had n number of points, so let's say if I had our beam, right? Okay, if I had a beam, then I could have some y1, y2, y3, y4, so on till yn. So I have y1, y2, y3, y4, so on yn. Okay, so if I want to say if there's a y1 displacement, what is the force F1? So the F1 or the force at point 1, so let's say what's the force at point 1, is influenced, or you can say think of it as a reaction force at point 1, is influenced by the displacement of each of these points independent of the other. Or I can say my F1 is K11 into Y1 plus K12 into Y2 plus K13 into Y3 plus so on plus K1n into Yn. Have all these n points. At each of these points I'm applying a deflection, and I'm trying to calculate what is the reaction force at a certain point, or a force at a certain point, right? So this is saying how stiff is the structure, or how much force do I need to apply this displacement at that point, right? If the structure is stiffer, then to get the same displacement I need to apply higher force. If I'm going to have a very flexible structure, Kij is very small, even a very small force will lead to a large displacement, right? So I have large displacement. So let's think of it this way. So I have F, okay, 1 equal to K11 into Y1. So let's take one term just to think about it. So if this is very small, let's say my force is same, right? Then this is going to be very large. Similarly, if one force is same, K11 into Y1, if this is very large, this is going to be very small. Okay, right? So intuitively it makes sense. On the left hand side we have the same number. So for example, if this was 10, right? If K was very small, 0.1, then Y1 would be 100. So I have the same force 10, and this is, let's say, 100. This is going to be 0.1, right? So in some way it is measuring how stiff is the structure, right? And how much that gives you a metric of how much force do I need to apply to get the same displacement. Or in matrix equation, so essentially we can write F1 equal to K11 into Y1 plus K12 into Y2 plus so on plus K1n into Yn. Similarly, I can write F2 equal to K21 into Y1, K22 into Y2 plus so on plus K2n into Yn. Or similarly, I can write Fn is Kn1 into Y1 plus so on plus Knn into Yn for all the n number of points. Or I can recast this as a matrix equation where I have some k into y, right? So this is nothing but my force vector, nothing but my stiffness matrix, nothing but my displacement. Now you might ask, if you go back to our equation of motion, Do you remember that we had mass into acceleration plus stiffness into displacement equal to forces? And suddenly you are telling me that I don't have this mass into acceleration term, I have only stiffness into displacement is forces. So it is important and pertinent to note here that we are only talking about a static deflection. So for this purpose of getting the stiffness matrix, we are assuming what if we don't have a dynamic load, but we had a very static load. So I'm going to apply a very slow load and calculate this stiffness matrix. Okay, so that is why you don't have the mass into acceleration terms at the moment. Alternatively, a more easier one to also calculate is known as flexibility influence coefficient. Okay, so flexibility influence coefficient, or known as IAIJ, let's again write the definition, is defined as displacement at any point I okay due to unit force at any point J with all other points fixed. Right? Or right, so essentially we are basically saying, we're kind of saying the opposite. If I had a displacement, if I had applied a force, what would be the displacement, right? Or Aij can be defined as if I had a displacement into the force. Okay, or let's write it more clearly or correctly. I is Aij into Fg, right? So why, we'll see why this is very interesting, why we want to use the flexibility coefficient rather than the stiffness coefficient. And similarly, like earlier, we can write y1 equal to a11 into f1 plus so on a1n into fn. Similarly, I can write yn is an1 into f1 plus an2 into f2 plus so on plus ann into fn. Or I can recast this again as a matrix equation as y equal to a into f, right? So we already know this, we have already defined what these terms are, but let's try to again rewrite them for our, to recap things. So there's nothing but our force vector, our displacement vector, and there's nothing but our flexibility matrix. We will see why this is interesting to us, why we are interested in this flexibility matrix. Again, if you go back and see, so we had y equal to a into f, or we also had written f is equal to k into y, right? So they're both correct, which also means that our stiffness matrix is nothing but the inverse of our flexibility matrix. So inverse, right? So if we know the flexibility matrix, we can invert to get the stiffness matrix. And if we know the stiffness matrix, we can invert to get the flexibility matrix. So now why is this interesting? Before we move ahead and try to do all the math and jumbo mumbo, we'll try to understand why is this interesting and why do we want to do this. Okay. So if we go back to some of our equations that we wrote, so we said that we had this cantilever beam, right? So we have a cantilever beam and we have some points. Let's say we had some point 1 where we had m1, point 2 where we had m2, and point 3 where we had m3, right? Now, so now if I was to apply a load P1, a concentrated load at point 1, then from my structures 1, I can write my moment at any x, right? So this is our x at any point x, right? Any x moment at any point x is nothing but P1, which is the force, into the moment arm, which is L minus x. And also I know from structures 1 that if I know this, I also know my m is nothing but E into I into d square y by dx square, right? That means also my deflection y for this scenario is given to be P1 by EI into Lx square by 2 minus x cube by 6. Okay, I'm not going to go and derive how we got this. What I would request you to do is go back to your structures 1 module where you did beam deflections and try to understand how to get the deflection at any point where if you have a point load. If I have a point load, I can find a deflection at any point in the beam, right? So that means now if I know this, so this is, let's say, if I know deflection at any point y, then that means that I can do y by P1. That would give me my flexibility coefficient. So what's, if you remember back, our flexibility coefficient, so let's keep writing it here. Y is nothing but divided by the force. That is nothing but my flexibility coefficient. So let's say point into 1, right? So this some point. So y at some point, let's say, let's call it some point beta, right? Is nothing but the flexibility coefficient beta. That means if I have this cantilever beam and if I'm going to apply, let's say, think of our cantilever beam. Now I'm going to fix this. I'm going to apply a load at some point P1. I'm going to calculate what the deflection is at point P1, point P2 and the point P3. That gives me 3.3 items on my flexibility matrix. Now if I now go back and apply a load on P2 and calculate what is the deflection at P1, P2 and P3, I get 3 more. If I now apply a load at P3, then I know again what is the flexibility coefficient of again 3 more items on the flexibility matrix. That means totally I have a 3 cross 3 matrix, and by applying a load at each of these points and determining the deflection at each of these points, I am able to find what my flexibility matrix is. So once I know what my flexibility matrix is, I can invert it to get my stiffness matrix. So let us finish completing the batch to determine how to get this flexibility matrix and how to invert it to get our stiffness matrix. Okay. So we have, if you go back to our original case, so we had a cantilever beam. So we have a mass M1 here, a mass M2 here, and a mass M3 here. So let's assume that we are applying a load P1. So we have Y1, Y2, Y3. So our goal is to determine what is Y1, what is Y2, and what is Y3 under the influence of load P1. Okay. Then secondly, then after this we do this, we'll go and try to now change the scenario, and we have the same M1, M2 and M3 with Y1, Y2 and Y3. And we are going to apply a load P2 instead at point 2, right? And then we are going to determine what is Y1, what is Y2 and what is Y3. Again under the influence of load P2. Okay, so once we complete this, we are going to again do the same thing. I'm repeating this a bit here, but just so that we understand the process. P3, Y3, Y2, Y1. We are going to apply a load P3 to determine again what is Y1, what is Y2, what is Y3 under the influence of load P3. If we are able to do this, so you can see 3 plus 3 plus 3, we are going to be able to get the 9 components of the flexibility matrix. In order to do this, we'll leverage some of the understanding that we have from our structures 1 module, where we have already determined, if we had a cantilever beam, what would be the deflection at each of these points given the load moment and the deflection curve. Okay, so let's start by the first scenario. So first scenario where we have applied a load P1. So we have applied a load P1 and we want to determine Y1, Y2, Y3, right? So our flexibility coefficient A11 is nothing but Y1 over P1. Similarly, our flexibility coefficient A21 is Y2 over P1 and A31 is nothing but Y3 over P1. So from structures 1, we know for point load, right? So deflection at the tip here, the deflection is, as we talked about earlier, we set the moment and from there we can integrate it twice in order to get the deflection equation. So deflection is nothing but P1 over EI into Lx square over 2 minus x cube over 6, right? So that means our Y1 is equal to Y at x equal to L. I'm not going to do all the math here. I'm let you to substitute and try it out. I get P1 L cube over 3 E I. That means my flexibility coefficient A11 is nothing but Y1 over P1, that is L cube over 3 EI. So I'm going to do the same thing again here. Because I have equal segments, I can write Y2 is nothing but Y at x equal to 2L by 3. And if I substitute that, I get 14 P1L cube over 81 EI, which means my A21 is Y2 over P1, nothing but 14L cube over 81 EI. Similarly, I can get my Y3 is nothing but Y at x equal to L by 3. That is nothing but, if I substitute again, I get 4P1L cube over 81 EI. I would kindly request you to try to substitute and extract these yourself, and so that you can be sure of what you are trying to do here. 4L cube over 81 EI. Okay. So this scenario 1, let's say we call this scenario 1, was reasonably straightforward. And now if we are going to write our A, we have lots of terms we don't know yet. We'll fill in the terms that we know, right? I'm going to pull out L cube over EI outside, right? So I have L cube over EI. Right? I have first column I have available 1 by 3. I have 14 by 81 and 4 by 81. I still need to fill several things. As we go along, we'll try to fill them. Okay. So once I have a full matrix, that means I can get my stiffness matrix, which is what I need for my equation of motion, to solve that by taking the inverse of the flexibility matrix. Okay. So let's consider now the scenario 2. Right, where now we assume instead we are going to apply a load. Okay, maybe I can make it look better at P2. Again I have Y3, Y2 and Y1. So now the moment acting at any point X, right, on the left side of this load, I can write, there's no moment acting on the right side of the load. If you remember your structures 1, let's say if we have this beam, let's go back and try to look at the scale that I have here. if I look at this beam, if I'm going to apply a load here, everything on the right side of this load, which is this side, and anything on this side experiences some bending moment, but everything on this side is just undergoing a rigid body rotation. Right? There's no real deflection or change in shape. It is just moving in a rigid body manner. So everything along here is just rotating about this point. Right? Everything up to this point is deflecting because there's a bending moment, and everything here is just rotating in a rigid body manner. Right? So we need to rewrite our moment equation. So our moment is nothing but P2 into 2L by 3 minus x. Okay, that means if I'm going to substitute L here, I'm going to have a negative moment. If I just substitute 2L by 3 minus L, it is saying me that I have a moment in the opposite direction, which is not true. Right? So this equation is only valid for that section of the beam until where the load P2 is applied. On the next further rest of the segment 1, there is no moment acting. Moment acting is 0, so there's only rigid body motion. There's no real rotation, deflection. So again, I know if I integrate it twice and I can calculate this, I'm going to leave this to you to go back and look at structures 1, where you have already done a big part of this. You would get 2L into x square minus x cube. Right? So if you're going to say, if you substitute x equal to L, which is the tip of the beam, you'll see that the deflection is 0, which is not necessarily the case. Right? So this equation gives you the deflection only to the that part of the beam on the left side of this load, not on the other side of the load. Okay, so this makes it very straightforward. Now I can just substitute, so I can get y2 is nothing but y at x equal to 2L by 3. I can easily substitute that. Similarly, I can get y3 is y x equal to L by 3. Both of these points are on the left side of the load, or at that point where the load is applied. We'll come to how to deal with the y1, right? So we'll come to deal with that. If I'm going to substitute that, I get 8 P2L cube or 81 EI. That means my flexibility coefficient A22 is nothing but y2 divided by P2 is 8L cube or 81 EI. And similarly here, if I substitute L by 3, I would end up getting 5 P2L cube or 162 EI. Or I can say my flexibility coefficient A32 is Y3 over P2, which is nothing but 5L cube or 162 EI. Right? So, but then I still want to calculate what would happen to the point y1, because I need also the ya1, 2 as well, right? So, going back to what we did, so we said, let's just go back here and just look at our ruler. We said we have fixed this end. We're going to apply a load here at some 2 by 3, and rest of the beam is moving in a rigid body manner. So whatever was the slope of the beam at this particular point, that same slope is basically being continued here. So if I know the slope of the line, I know the horizontal distance, I can say further what is the y additional change in displacement of this point y. Or in other words, I can say my y1 is nothing but deflection at y2 plus the slope of the line at x equal to x2 into the length of the segment. Right? So all I have, let's go back here. So all I have is the deflection at the point y2. I know the slope of this line. The slope of the line is not changing because there's no deflection. I know the horizontal distance between point 1 and point 2. I know the slope of this line. That means I know from the point y2 what is the additional change in the position of this point y1. Right? So if I'm going to substitute everything back here, I have, so I can just substitute here just to be sure. I have L segment is nothing but, so y2 is nothing but 8p2 p2L cube over 81 EI. Plus I'm going to leave it to you to calculate the slope. You know why? So you can differentiate by x, and I'll leave it to you to calculate the slope and calculate that and substitute x equal to 2L by 3 into L by 3. So if you would do this, we would be getting 14 P2L cube over 81 EI. Or in other words, my flexibility coefficient A1 2 is nothing but Y1 over P2, that is nothing but 14L cube over 81 EI. Now let's try to populate all the things that we found into our flexibility matrix that we have here, right? So let's try to copy this. And we'll try to paste it out here. So we have some new terms available. A12 is 14 over 81 because we have removed out L cube over EI. So we have A12 is nothing but 14 over 81. Then we have A22 is 8 over 81. And A32 is 5 over 162. Okay, 5 over 162. We have been trying to fill our flexibility matrix, so that once we know that, we can calculate, take invert of it and try to get the stiffness matrix. So last we are left out with our scenario 3. Our scenario 3 is where we are applying I'm not going to write M. We already know that's M3. So Y2, Y1. So we're going to apply a load P3 here. Very similar to what happened last time, our moment needs to be rewritten as P3 into L by 3 minus X. So as you can see, again, just the same thing as what we did in P2, that everything to the left of this load, where we have between the load and the hub, is where you might have a moment. On the right side of it, you don't really have a moment acting. So we need to again be careful, like how we did previously, in order to calculate it. Or you can get y equal to P3 over 6EI into Lx square minus x cube. Okay. So if I'm going to use the same idea here, I can easily write y3 by just substituting y at x equal to L by 3. And I'm going to get P3 L cube or 81 EI. Or I can write my flexibility coefficient A33 as Y3 or P3, which is L cube or 81 EI. Right. But now I have to again think about my Y1 is nothing but Y3 plus dy by dx, which is the slope, at x equal to L by 3 into two length segments. So distance between the point and point 1, point 3 and 1 is 2L by 3. Right? So I'm going to leave it to you to rewrite this just like how we did previously. You can substitute to get the same thing. That means I get my y1 equal to 4p3l cube over 81 EI. If I'm going to substitute and simplify, that means that my flexibility coefficient A13 is 4l cube over 81 EI. Similarly, I can write my deflection 2 at point 2 is y3 plus dy by dx at x equal to L by 3 into L by 3. So distance between point 2 and point 3 is only L by 3, not so we use that accordingly. And again, if I simplify this, I get y2 equal to 5L cube or 162 EI. Or I can say my flexibility coefficient A23 is 5L cube. So there's also P3 here into 162 EI, because there's nothing but Y3, so Y2 over P3. Okay, so now let's try to copy back our flexibility matrix and try to see if we can fill up the rest of the matrix, right? And see how to go ahead with that. So finally, if I'm going to start to fill in things that we already have done, so I'm going to write A23 I already have A23 here. A23 is nothing but 5 divided by 162. A13 is 4 by 81. And A33 is 1 by 81 if I'm correct, right? Okay, so one thing that we might want to notice at this point is that, so there's a symmetry here. So let's try to highlight that symmetry. So let's say this number is same as this number, right? This is same as this, and this is same as this. That means we have what is the symmetric matrix. That implies A is a symmetric matrix. That implies also our stiffness matrix K is a symmetric matrix. I mean, there are scenarios where it might turn out to not be symmetric matrix, but for a purpose of our module, we can assume that we have a symmetric stiffness matrix, and there's no other effects in it. So now that we know our I'm not going to do the invert. I mean, the inverted matrix is available in the lecture notes. So now, if we go back to our goal was to write the equation m into x double dot plus k into x equal to 0. So we have been able to get our M mass matrix, we have been able to get our stiffness matrix, and we should be able to get our overall from here, we should be able to get our goal to get the natural frequencies of the system. Okay. So let's stop here and we'll pick up from here in the next lecture.